Today let's talk about absolute value. Let's define the absolute value first. The absolute value of a real number a, denoted by bar a, is defined by For example, the absolute value of 5 is the value 5, because 5 is greater than or equal to 0. The absolute value of 0 is obviously 0. The absolute value of negative 3 is negative of negative 3, which is 3. Let's prove this theorem. The absolute value of AB is equal to absolute value of A multiplied by absolute value of B. If either A or B is 0, both sides are equal to 0. If A is greater than 0, B is greater than 0, then AB is greater than 0. So the absolute value of AB is just AB itself. It's equal to A absolute value and the absolute value of B. If A is greater than 0 and B is less than 0, then AB is less than 0. So absolute value of AB is equal to negative AB, which is equal to A times minus B, which is equal to A absolute value and B absolute value. The remaining cases are treated similarly. Theorem B. Absolute value of A squared is equal to A squared for all A as a real number. As A squared is greater than or equal to 0, we know that A squared is equal to the absolute value of A squared, which is equal to A times A and then absolute value, which is equal to A to the absolute value and then squared. Theorem D. Minus absolute value of A is smaller than or equal to the value of A, which is smaller than or equal to absolute value of A for all A as a real number. If A is greater than or equal to 0, we know that A is equal to absolute value of A. Then A is less than or equal to the absolute value of A. Also, A plus absolute value of A is greater than or equal to 0. So negative of absolute value of A is less than or equal to A. If A is less than 0, negative A is equal to the absolute value of A. So negative of absolute value of A is equal to A. So negative of absolute value of A is smaller than or equal to A. Also, absolute value of A minus A is equal to minus A minus A, which is negative 2A, which is greater than 0. So absolute value of A is greater than or equal to A. Theorem C. If C is greater than or equal to 0, then absolute value of A is smaller than or equal to C if and only if negative C is smaller than or equal to A is smaller than or equal to C. Now assume the absolute value of A is smaller than or equal to C by theorem D. we have this inequality. Since the actual value of A is smaller than or equal to C, we know that the actual value of A is greater than or equal to negative C. So negative C is smaller than the actual value of negative A, is less than actual value of A is smaller than or equal to C. So negative C is smaller than or equal to A is smaller than or equal to C. Now so negative C is smaller than or equal to A is smaller than or equal to C. Then A is smaller than or equal to C, and negative A is smaller than or equal to C. As the actual value of A is equal to A, or actual value of A is equal to negative A, and we know that both A and negative A are smaller than or equal to C, we have the actual value of A is smaller than or equal to C. Now let's prove the triangle inequality for real numbers. Let A, B be real numbers. Then A plus B and the actual value is smaller than or equal to actual value of A plus actual value of B. From theorem D, A is bounded by negative actual value of A and actual value of A, and B is bounded by actual value of B with minus sign and actual value of B. By adding these two inequalities, we have, by theorem C, actual value of A plus B is smaller than or equal to the actual value of A plus actual value of B. Now let's show the reverse triangle inequality. The actual value of A minus the actual value of B is more than or equal to the actual value of A minus B. Actual value of A is equal to actual value of A minus B plus B, which is more than or equal to the actual value of A minus B plus actual value of B. Then actual value of A minus actual value of B is smaller than or equal to actual value of A minus B. Similarly, actual value of B is equal to actual value of B minus A plus A, which is less than or equal to actual value of B minus A plus actual value of A. And we know that actual value of B minus A is equal to this value. We know that actual value of A minus actual value of B is greater than or equal to the minus of actual value of B minus A, which is negative of the actual value A minus B. Now we notice these two equations. By theorem C, actual value of A minus actual value of B is smaller than or equal to the actual value of A minus B. Let's introduce a corollary. We know that by the triangle inequality, since A plus B and then actual value is smaller than or equal to actual value of A plus actual value of B, by induction, we have actual value of A1 plus A2 plus blah 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 plus AN is smaller than or equal to A1 plus A2 A2 plus blah 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 plus AN. if a1, a2, blah 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 to an are real numbers. A convenient and familiar geometric interpretation of the real number system is the real line. In this interpretation, the actual value of an element A in the set of real numbers is the distance from A to the origin 0. More generally, the actual value of A minus B is the distance between A and B. Let's prove a lemma. Let A be a real number if 0 is smaller than or equal to A is less than or equal to epsilon. For any epsilon greater than 0, then A must be equal to 0. Assume that A is greater than 0, then A over 2 is greater than 0. Since A is less than or equal to 0 holds for all epsilon greater than 0, take epsilon to be the value A over 2, then A is less than or equal to A over 2, which implies A is less than or equal to 0. This is a contradiction because we assume that A is greater than 0. Contradiction arises. So A is greater than 0 is false. Since A is greater than or equal to 0, and we know that A is greater than 0 is false, so A is 0. Definition. Let A be a real number and epsilon be a positive real number, then the epsilon neighborhood of A is the set. So we know that for a real number x belonging to this epsilon neighborhood, it's equivalent to say that x minus A actual value is less than epsilon, if and only if negative epsilon smaller than x minus A smaller than epsilon, if and only if A minus epsilon is smaller than x is smaller than A plus epsilon. This is the epsilon neighborhood. Let's prove a theorem. Let A be a real number if x belongs to the neighborhood V epsilon A for all epsilon greater than 0, then x is equal to A. Proof. The actual value of x minus A is less than epsilon for every epsilon greater than 0, then x minus A times actual value is equal to 0. So x minus A actual value is 0, which implies x is equal to A. This is the end of the video. If you find my video interesting, please consider subscribing my channel, liking my videos, and commenting down below. Thank you. See you in the next video.